Today we're going to be talking about horizontal and vertical stretches. So far you guys have learned how to do translations, so moving graphs left and right and up and down, and you've also learned about reflections. The good news is that for horizontal and vertical stretches, we're working again, just like with reflections, with the A value and the B value when we're in function notation. So a vertical stretch is going to make a graph either shorter or taller, so the y values are changing, and a horizontal stretch is going to make a function either narrower or wider, and it's a change in x values. So like I said, again, we're looking at A and B. So remember, in the previous lesson, we looked at when A and or B were negative. So we looked at situations like this, where we would have a vertical reflection, and we looked at situations like this, where we had a horizontal reflection. Now we looked at them more commonly without that A value there, or without that B value, because the A or B value was just 1, so we didn't need to include it. But today we're going to look at when those A and B values are a coefficient other than 1. So to start, the A value represents a vertical stretch. So this A value in front is going to make the graph get longer or shorter. It's going to either stretch or compress the y values. If this A value is larger than 1, the graph is going to get taller. If it's between 0 and 1, the graph is going to get shorter. So for example, if we had g of x equals 1/2 f of x, it means the y values are being split in half, so the graph would get shorter. Whereas g of x equals 4 times f of x means the y values are being multiplied by 4, or the graph is getting taller. Just like we've seen in the previous lessons, for the b value, we're talking about a horizontal stretch. But again, horizontal movements always look the opposite of what they are. So for example, if we have g of x equals f of 1/2 x, this graph is actually being stretched by a factor of 2, whereas this graph is actually being compressed by a factor of 2 or stretched by a factor of 1/2. So again, for this first function, the x values would be multiplied by 2, and in this graph, the x values would be multiplied by 1/2. So if we look at example 1, I've started with a basic parabola. In the first parabola, we have y equals 3x squared. Remember, x squared represents f of x. It's just the function. Because the 3 is in front of the function, this would be a vertical stretch by 3. All you're going to do is take the y values on the graph of x squared and multiply them by 3. So you'll see in pencil here, I have the graph of y equals x squared. 0, 0, 1, 1, 2, 4, etc. I've taken the y values and multiplied them by 3. So the y value of 0 times 3 just stays there. A y value of 1 times 3 moves up. And a y value of 4 times 3 would be 12, which is off of the graph. So there's my new function. I do the same thing on the other side. So this graph has gotten much taller. For the second one, I've got y equals 1/2 x squared. So this is a vertical stretch by 1/2. And the x values are being either, you can think of it as divided by 2, or think of it as multiplied by 1/2. Both of those things mean the same thing. So instead of 1, 1, I now have 1 and 1/2. Instead of 2, 4, I now have 2, 2, because I'm dividing the y values by 2. So this graph ends up looking wider. Example 2 again deals with vertical stretches, but in this case, I've given it to you in function notation. So you'll see for part A, I again am showing a vertical stretch by 2, or the y values being multiplied by 2. Instead of giving you a function, I've just drawn the function for you. So I went along this wave and I selected the most important points, the key points here, and I multiplied these values by 2. Notice that anytime the y value is 0, it stays in the same place. And for B, we've got half of f of x, so it's a vertical stretch by 1/2, and we take our y values and divide them by 2, or again, think of it as multiplying by 1/2, either or. So these y values here shrink down to 1/2 and -1/2. Notice when I do these vertical stretches that the x values aren't changing. None of these points are moving from left to right. They are only moving up and down. It's because this is only a vertical stretch. In example 3, we've got a horizontal stretch. You'll notice the difference between this example and the examples on the previous page. Here, this a value is not in brackets, whereas in example 3, this is a b value because it is in brackets. This is 2x, all in brackets, to the power of 2, whereas the other ones were 2 times x squared. So notice the difference there. In this case, this is a horizontal stretch, but remember, I always do the opposite. So it's actually a horizontal stretch by 1/2. Or we take the x values and divide them by 2, or multiply by 1/2. Remember, that means the same thing. I've written out the mapping notation for you, just so you have it. But really, what ends up happening here, the pink graph here is y equals x squared. So the point 1, 1 becomes 0.5, 1, because I've divided by 2. The point 2, 4 becomes 1, 4. And the same thing on the left side of the parabola. In mapping notation, you'll see that I've gone from having the point xy to having the point 1/2 x, and y stays the same. So if you wanted to write out all your coordinate pairs, you'd see I'm just taking the x value and dividing it by 2. So it's splitting, and where it's 0, 0, it actually ends up staying the same. So this graph, a horizontal stretch by 1/2, this graph is actually getting narrower than the original. Very similar for example 4. So in example 4, in this case, I've got mapping notation again for you. So use the graph of f of x, which was drawn for you in black, to sketch y equals 2/3 f of x. So very similar here with our mapping notation is I figured out this is a vertical stretch by 2/3 because this 2/3 is outside the bracket. If it was inside, it would be horizontal. Then I'm taking my y values and multiplying them by 2/3. So because this is a fraction, mapping notation can be helpful. What you'll notice here is you're going from -4, 0, and when you multiply y by 2/3, it doesn't change. -2, -3, the -2 stays the same, and -3 times 2/3 is -2, etc. Do that for all of the points. Then, when you graph them, you'll notice that there's 3 points here that did not change because their y values were 0, and this minimum and maximum, just moved in a little bit. So went from -3 to -2, and +3 to +2. finally, in example 5, this is a spot where lots of students get confused. So I've got two graphs on this grid here. I've got g of x, which is this narrower wave, and I've got f of x, which is the wider wave. I'm asking you to state first g of x in terms of f of x. So what that means is I want to know, how do I get g of x from f of x? So f of x is the original graph. How do I get g of x? So what I did was I picked a point on the original graph. I just happened to pick this point here for this original curve f of x. I picked a minimum, and I picked that same minimum on g of x. So what I noticed was that these points are related to each other. This one's -1, this one's -3. I could have also picked any point. I could have picked a maximum. I could have picked one of these midline points. I chose to pick something that had a y value that wasn't 0, because remember, or an x value that wasn't 0. Remember, x or y values of 0 are tricky to work with stretches because they don't actually change from the original graph to the new graph. So I chose points that had x and y were both not 0. And I noticed that between the two of them, you either had to multiply by 3 or divide by 3 to go back and forth. So when I'm trying to take f of x and get g of x, I need to go from f of x, so here, to here. The x value is what's changing. The x value is going from -3 to -1, which is like dividing by 3. But again, this is a horizontal translation, a horizontal stretch. So when I put this into my function notation, it looks the opposite. I'm dividing my x value by 3. When I write it in function notation and put it in the bracket, I write it as times 3. The opposite is true for b. For b, I'm trying to do something to g of x to this point to get this point, which is times 3. But again, this is a horizontal stretch. So when I put it in function notation in the brackets, it is g times 1/3 of x. That wraps up horizontal and vertical stretches. In the next lesson, we're going to put all 4 of these types of translations, reflections, and stretches together.